Hello, this is Jack Jackson. In this video, we're going to be introducing line integrals over a vector field, or line integrals of a vector field. So in the previous sections, we introduced line integrals of a scalar function over a curve in 2 or 3 dimensions. In this section, we'll introduce a second kind of line integral. This time it will be over a curve in 2 or 3 dimensions, but the integrand will be a vector function. Before we get started, let's take a look at oriented curves. So recall that when we parameterize a curve, it obtains a directional orientation. So if we move forward along the curve as values of the parameter, say time, increase, and this is called an oriented curve. For example, the curve that you see graphed here to the right has the orientation indicated by the arrows. As t increases from 0 to pi, which is our domain for t, we start at the origin, 0, 0 for x, y, trace out the curve going in this path going along here, and we end up down here at the final point when t is pi of x is 0 and y is negative pi square. Our vectors, remember, are vectors going from the origin to a point x, y on the graph of that curve, and the x's are given by 3 sine of t and y is given by t squared cosine of t for this specific example. So basically remember that paths that we have of curves, parameterized curves, have a direction to them. Okay? The opposite of this curve would just be reversing the arrows. It would start down here and end back up here at the top. So the basic idea of a line integral over a vector field is adding up the product of the amounts of displacement along the curve and the portion of the vector field that's acting in the same direction as the curve. That's an intuitive idea of what's going on. So one good way to introduce this is by considering an important application, and that's calculating work. So let's talk about work just a little bit. In physics, there's a specific definition for the term work, and that's the context that we're doing now. Not work like I'm working when I'm making out this video, or work when you're going to your job, but work in the sense of physics is what we're talking about here. So if a constant force F is applied to an object and it moves a fixed distance d, then the amount of work that is occurred is just that force times that distance. So work is force times distance. Now, we're assuming there the force is applied in the direction that we're going at a constant force. We move at a fixed distance in that direction, just force times distance as a scalar function. But in reality, force and distance really, force and displacement are actually vector quantities. So if a force is applied which is perpendicular to the motion of the object, it does not contribute anything to the work. But a constant force vector applied at an angle to the direction of the motion can be resolved into normal and tangential components. So the perpendicular part doesn't affect the work that's done, but the part that's going in the same direction in the motion is going to affect things. So the work done is then the product of this distance the object has moved, or the size of the displacement vector, times the norm, or the size of the tangential component of this vector. So in the illustration you see to the right, we move a point from an object of some kind from point A to point B in that direction, and we do it by applying this force at some angle here. So we resolve that into components so that we have a normal component, which is really irrelevant, and the relevant tangential component, or the component in the same direction. In other words, this component down here is the size of just the projection of this. So you're projecting this vector onto the line AB, and that gives us this purple projection vector, which is a projection of this force vector. Now we just take the size of that of this force vector times this distance, and that gives you the work done. So one way to see it, anytime you can see a product, we can always see it as an area of some rectangle. And so the rectangle we need is to take this this purple length and rotate it up so we get a right angle here. And you can see that this length here for that component is the same as this length here, and then we get the area there. So that area is exactly what is meant by the dot product, right? So the force dot the displacement vectors is in fact the amount of work done. Okay, so let's just take a look at that here just a minute. Let me put this back over here, and I want to look at this where here's our situation that we have here. So I'm going to make this dynamic so this moves around. These are the vector components here, and we can see that the component there is always the projection is always going to either go in the same direction or the opposite direction. When it's in the opposite direction of the motion, then we get a negative dot product. That's not going to really make sense for a work situation. But we have this here, and so it has to do not only with the length of that red vector, but the angle it makes with the direction. Now, if you're just going strictly in the direction here, you're just multiplying the norms there together. The displacement vector, that's the distance from A to V, or the vector going from A to V. Take that, dot product that with the force vector. It's just those two magnitudes multiplied together. But if we're going off at a different angle, that can make a difference of what we end up with. Okay, so in the next, well, throughout this video actually, we're going to be looking at a specific example, and here is the example that we're looking at. We're going to be investigating the work done in moving an object along a curve when a variable force is acting on it, and that the force vectors are different depending on which points we're at. So, for example, you can see a few of them graphed here in red on the left side of the screen. So I just had, well, it's just 4 of the vectors, but there would be one of these at every point in the plane, or at least every point along the curve. And the force would be given by y, comma, minus x. And so that force field gives us this vector field, which we've got a few vectors from that vector field graphed. The curve then is given by the position function. R of t is 1 plus 4 sine of pi over 2t, comma, 2 plus 2 cosine of pi over 2t, and we're going to let t go from 0 to 1. And so here you see several position vectors. Remember, position vectors are vectors like this. Start at the origin, they end at the point here, x, y, and they're given in functions of say, time, t. And so we can see that these are parametric equations for x and y. That's what we use to define these things here. So we have position functions, a function which you just saw that's going to define these vectors, which in turn defines this curve. And here are some force vectors. What I've actually done is I've picked some equally spaced t values at t equals 0, t equals 1, but then also at fourths. So t equals 0, t equals 1/4, t equals 1/2, t equals 3/4, and t equals 1. And I actually just have the vectors filled at 4 of those, at 0, 1/4, 1/2, and 3/4. And you can see those velocity vectors. I mean, not velocity vectors, but force vectors, v. So values of our function f, or vector field. So we want to consider the work done in moving an object along a curved path where the variable force is applied along the path. We can approximate the work done by dividing the curve into smaller subcurves and approximate the work done moving the object from the beginning of that subcurve to its end by considering the force to be constant on that subcurve, say the same as it is at the beginning of the curve. So we want to find the dot product of that constant vector. It's not really constant, but we're going to pretend it's constant, right? And by the displacement vector for that between those 2 points. And we're going to do that, and that's going to give us an approximate amount of work going from the one point to a nearby point. We're going to do this for various points and add them up, and then that gives us a Riemann sum, where it'll sum up these dot products to get a Riemann sum, which is an estimate of the total work done. And then, of course, as always, we'll take a limit as you divide the curve into more and more smaller and smaller subpieces to get an integral for the work. Okay, so let's take a look at the here's some pieces of it. Displacement vectors are here. Across here, the pink ones, which it's an r minus the previous r sub k plus 1 minus the r sub k will give you the kth displacement vector. Force field is given by F, and we're going to see the dot product by projecting the force field onto those displacement vectors and then flip it around and make some areas out of it and add those areas up. Okay, so let's go back to the picture here. So let's start with just the curve. We're going to divide it up into equal pieces. So I have 5 points here. That's actually 4 pieces. Now remember, your position vectors are here, and so your displacement vectors are the differences. So this is R1, this is R2. R2 minus R1 is R1 is delta R1. And R3 minus R2 is this vector right here, which is delta R2, and so forth. Notice it takes 5 points to get 4 intervals. Okay, so I don't need the position vectors anymore. Let's turn those off. Okay, so we're looking at these displacement vectors. Okay, and here's our vector field. So there's just the vector field evaluated at the beginning of each of those 4 intervals. Now, of course, these vectors are actually changing as we move from this point to this point, so it's not constant. But we're going to pretend it's constant or approximate it with constant, assuming it's the same as it was to begin with, sort of a left Riemann sum kind of an estimate. Okay, so here are displacement vectors. So what we want to do is we want to do the dot product of all these things, the dot product of the displacement vectors and the velocity vectors. Now, one way to see that is by projecting the vector field, which in this case are force vectors, so that we resolve it into components in the direction of the displacement vector and then perpendicular to that. So if you look at that here, let's just pick one of them. Let's say this one right here. If you drop this perpendicular to here, this is a line containing these 2 points here, and it goes on out this way. If you drop perpendicular down here, we will intersect that line right there. So it's the tip here. Bring it down perpendicular to that line will give you the tip here. And then you have a normal component here, which I don't have graphed. Similarly, we take the red and project it onto the line containing these 2 pieces, and we get this green one, and so forth for the other 2. So now we don't really need the original force vectors. The vector field itself is not really as important. What's important is the components of that field that are going in the same direction as the motion of the object. Okay, and then we're just multiplying these 2 sizes, the size of the of this displacement vector times the size of that force, the component of the force in that direction. And that's exactly what the dot product of those two vectors will give you. So we went back to our actual vector field and just did the dot product of that with the displacement vector. We're going to get that area. Okay, so that's what we want to do. And then we just want to simply take those four areas and add them up. In this case, the sum of the areas, the sum of those dot products is 22.27. Now, if we want to make this a better and better and better approximation, then what do we need to do? We need to take smaller and smaller intervals, subintervals here, or subcurves, and then we want to have more and more and more of them, which will give us more and more rectangles. We add up those areas, and that should, the approach, as we take a limit, that should approach the actual work that's being done. So here you can see in the slide some of those same things. So here's some displacement vectors in pink, and the position vectors in blue, and the curve there. Here you see the curve along with the force field, at least the parts of it that we're using. Here you see the force field, and then the projections of the force field in the directions of the displacement vectors. So those are the green things. And then you take the green length times the, it's pink, the pink length, like here, and you get these areas of these rectangles. In this case, there are 4 of them. Okay, so we're summing that up, and we get the work done. So these rectangles, each one of these is just a force dot, a delta R. Now, of course, we take a limit of this Riemann sum to get a line integral over a vector field. I have a tendency to put this little circle here to indicate line integrals. That's optional. You don't have to have that. A lot of people don't use that. It's particularly used a lot of times when your path actually is a closed path. But I'm going to use it either way. So a line integral of f dot dr is what we come up with. So what we ended up with is a limit as the n goes to infinity and the delta r sub k's approaches 0. So the delta r sub k's are the change in displacements. Okay, and we're doing that dot product. That gives us an area of one of those rectangles that we had. We're going to sum those up, take the limit as the number of them goes to infinity and their widths go to 0. And that's going to be our line integral here, f dot dr. Now I'm going to show you an alternative approach. It's an alternative way to approximate the work. But this time, instead of projecting the force vectors from the vector field onto the direction of the displacement vectors, which are basically directed secant line segments, we will project the force vectors from the vector field onto the direction of the unit tangent vectors. So this will be in the direction of motion as defined by the tangent vector instead of a secant vector. And it works a very similar way. So let's hide a few things here. There's our curve. And so let's take a look at this a minute. Here are the position vectors. If you take the derivative of that function, you get r prime, which is the velocity vectors. And so I'm going to evaluate those at the 4 points, which are the beginning of my 4 intervals. And then what I want to do is cut those down to unit vectors, unit tangent vectors. So I'm going to cut them down to the length of 1, expand or contract so that we get the length of 1. So those basically just contribute direction only. And so that identifies the direction that we're moving at instantaneously at these 4 points on the curve. That's the tangent vector, unit tangent vectors. Now here's our vector field at those 4 points, and what we want to do this time again is project them, but this time how we define the direction of the motion is by that tangent vector. So we're going to project them onto the tangent vector. So these are the tangential components of the vector field at these points. And then the just take one of them, like say this one, whatever. Say this one and this one. So if you took that unit tangent vector, extended out to a line, dropped a perpendicular here, it would go through this point, and then we would get that resulting component for that particular thing. So this is the important part of the red vectors or the purple vectors, right? It's the part that's actually pushing the object forward, whereas the normal component we also have, like for this one here, let's see, there's a normal component here as well. Okay, but it's not affecting the work done. So I can get rid of these, and I'm only really concerned with the amount that's pushing in the direction of the motion. This time the direction of the motion is defined by the tangent vectors. Okay. Now we look at the dot products. We're going to take these displacements here and multiply them by the lengths of these purple vectors. And that gives me, again, some areas of rectangles, 4 of them in this case. And the sum of those areas is 21.6 in this particular case. Okay. All right. So let's go back to here, and we see kind of the same thing. So their curve is r of t. Those are the position vectors. The velocity vectors are the derivative of the r vectors, or what you see in black there on that picture. And the unit tangent vectors are the shorter vectors that you see in black. They're all unit 1, but they go in the direction of the tangent to the curve. Here's our vector field at those points in red. And if we project those into the same direction as the motion given by the tangent vectors, then we get this. And that is actually, so we get that tangent component. And then we find the work done by multiplying those the lengths of those purple vectors by the amount of displacement, which is a delta S, using our notation from earlier. Now, what we can do is kind of interesting. We do get rectangles here, right? So why don't you think of doing, see if you can visualize this. Take this rectangle, rotate it up in where this point is above that, is there, and that one stays where it is. But then it's standing straight up towards you in the plane. So now it's perpendicular to the XY plane. And then do that again for this one, this one, this one. If you stand those up, you get a shape that looks like this. Okay, and if you do this, now we're interpreting this the same way we did the line integral of a scalar function. Scalar field, okay, not a vector field. So the scalar function that we're integrating is f dot t. So this line integral here is like we did, I think, in the previous video, or a couple of videos where we did line integrals over a scalar function. It was some scalar function ds, and then to integrate that over the curve. So that was f dot t vector is our scalar function, and then that's with respect to the arc length parameter s. So looking at it this way, here are several examples of the Riemann sums. So this is before we take the limit. This first one has 4 subdivisions. I don't remember how many are in these here or here, but more, right? More here and even a lot more here. And you can kind of visualize that limit process going on, because we want to take the limit as the number of those little subdivisions, which generate little rectangles ultimately, goes to infinity, and the widths of them all go to 0. Notice that the widths of these things are not necessarily the same here. You can see that here and back here. These widths here and here and here and here are not the same, because in this case the t's are evenly spaced, but that doesn't make the delta s's all the same. But nevertheless, we get an area of a wall just like we did before. So this is another way to visualize it. So we have the integral of f dot dr is a way I normally think of it in terms of a integral over a vector field, the line integral over some curve C. But it's equivalent to a line integral over a scalar field, where that scalar field is f dot t. But then, ultimately, if you want to do these, the ultimate idea is we want to get them in terms of a parameter t, so we can turn it back into a calculus 1 or calculus 2 integral. So this is just integral of a real valued function over here, a single variable integral, and the last. And basically the f is here, which is f of r of t. So you get f, which might be given to you in terms of, say, x and y. You ultimately get it in terms of t. And it'll be a vector. Then you have your r prime vector. We do a dot product, and then that will give us the thing we're wanting to integrate. And then ultimately that's a function of just t alone. And then we do the integral, which is a good old Cal 1 problem now. Okay? So let's go back to our example. We want to compute the work done in moving an object along the curve C when a variable force is given by a vector field F is applied, where the curve C was r of t is 1 plus 4 sine of pi over 2t, comma, 2 plus 2 cosine of pi over 2t. And t is going to run from 0 to 1. And the force being applied is y, comma, negative x. And here are the details worked out. Okay, so again, here is the what we have here. The velocity or r prime function is just take a derivative here. So the derivative 1 is 0. Derivative sine of u is cosine of u times the derivative of u. So we get a pi over 2 times the 4 is 2 pi. So it's 2 pi cosine of pi t for the x component. For the y component, we take the derivative with respect to t of this part. So derivative of 2 is 0. Derivative of cosine of u is minus sine of u times the derivative of the inside is pi over 2 times the 2 is just pi. So we get minus pi sine of pi over 2t for the y component. F of xy is y, comma, negative x, but ultimately we need to get everything in terms of t. So we just do a little substitution. Y is 2 plus 2 cosine of pi over 2t, so that just becomes the first component. And the second component will be the opposite of what we had here for x, so distribute the minus, that's minus 1 minus 4 sine of pi over 2t. Now, the integral of f dot dr over this curve is the amount of work done. So what we do is we just take f, but get it in terms of t, so that's this 2 plus 2 cosine pi over 2t minus a comma 1, negative 1 minus 4 sine of pi over 2t. That goes here. Dot that with r prime, which is this vector right here. Then integrate with respect to t, dt, from t going from 0 to 1. So we need to do this dot product. So remember, it's the first times the first plus the second times the second. So it's just this term times this one here, plus this one times that one, which is what I have right here. Over here, I'm going to distribute this. So let's see, 2 times 2 pi is 4 pi, and then we got times cosine of pi over 2t. 2 times 2 is 4, and then you still got a pi from here. Cosine of the same angle multiplied together is cosine square of that angle. Now we have this part over here. And it is, let's see, multiplying these two parts. So this negative times negative becomes positive, and just 1 times that. So it's just pi sine of pi over 2t, but that's plus. And then we're just distributing here. So it's got a positive here, 4 pi, and that's sine squared pi over 2t. And then all the terms have a pi, so I'm going to factor that out front. And I'm going to put this term here, this 4 pi cosine square term, with the one that has the sine square together. And the pi's are gone now because I factored those out. Notice that this is 4. I can factor a 4 out of this, and I get cosine square plus sine square of the same angle. That's 1. So 1 times 4 is 4. So that kind of simplifies, which makes this integral a whole lot easier to do since we don't have to deal with any power-reducing identities. So this is a pretty straightforward calculus 1 integral where we just let u be pi over 2t, du is pi over 2 dt. And so this works out pretty easily. So the antiderivative here is we multiply by 2 over pi times the 4 is 8 over pi sine of pi over 2t. We have this one is the minus 2 over pi cosine of pi over 2t, and of course the 4 just picks up a t. So just check this by doing derivatives. The derivative of 4t is 4. Derivative of cosine of pi over 2t is minus, which makes that plus, sine of pi over 2t times the derivative of the inside, pi over 2 multiplies by the 2 over pi, cancels down to 1. Similarly, the derivative of sine of pi over 2t is cosine of pi over 2t times the derivative of the inside of pi over 2. Pi over 2 times the 8 over pi. Pi's cancel 2 and 8 cancel down to a 4. Still got our pi out front. Don't forget that. We're going to evaluate from 0 to 1. In fact, I'm going to actually just go ahead and distribute the pi because it makes this a little nicer by getting rid of these fractions. So multiply the pi inside, cancels these 2 pi's in the bottom, but this last term picks up a pi. Now we're going to evaluate from 0 to 1 by taking this expression, plugging in a 1, and then doing the same thing, plugging in a 0. Sine of pi over 2 is 1, so 1 times 8 is 8. Cosine of pi over 2 is 0, so this term is wiped out. And of course that's just 4 pi. Sine of 0 is 0, so that's a 0 term. Cosine of 0 is 1, so it's minus 2. That minus makes it plus 2. And of course that term's 0. 2 plus 8 is 10. So their answer is 10 plus 4 pi is the amount of work done. Or if we run that through a calculator, we'll get an approximation of 22.566, etc. that you see here. So there's an example of that. So hopefully that will give you an idea of what a line integral is when we talk about a line integral over a vector field.